Hi everyone. In this video we're still talking about differential equations, and we're going to introduce a technique for solving a differential equation using separation of variables. Okay, so what we're going to do is use integration to find a general solution of a differential equation. And then what we're going to do, if we're given an equation in which the derivative is equal to some other function, so you can see it right here. You can see that this is the other function, right? Then you can determine the original function by integrating both sides of the equation and solving for the constant term. So, plus c. So here's the deal. Remember when we found slope fields? We used a differential equation, right, to make a picture of all the slopes, no matter all the possible general solutions of the function, the differential equation. So here is the slope, right, that we used to create the slope field, but the picture of it looked like what it would be if we integrated it. So now all we're doing here in this, using this technique, separation of variables, is actually integrating it, and integrating it with an x and a y in it. Okay, so for instance, if I had dy dx is equal to 2x, right? I could integrate both sides, and I would integrate dy dx. Actually, what I would do is I would move the dx over here, right, and then integrate both sides. Well, if I integrated dy, I would end up with y, and if I integrated this, it would be x squared over 2, right, plus c. And so that's what we're after, is we're really wanting to do this. So here's the technique that we would use to find an equation for y in terms of x. So we've been given this differential equation right here, and we've been given an initial condition. And so what we want to do is a little bit like what we did on that last screen, is that we separated the variables. So for instance, if we start off with dy dx equals 3x over 2y, we want to put the 2y and the 3x together. So I'm going to multiply both sides by 2y, and I'm going to multiply both sides by dx, so that now I have separated the differential with y and the differential with x with its carrier, and then I'm going to integrate both sides. That's what this is. So this is going to be 2y squared over 2 equals 3x squared over 2 plus c. Now I have an initial condition, y of 0 is 10. So everywhere there's a y, I'm going to put a 10. And everywhere there's an x, I'm going to put a 0. And I'm going to end up with 100 equals c. So I'm going to end up with y squared equals 3 halves x squared plus 100. So here's another example. I've got dy dx equals 4xy squared. And so once again, I need to separate the variables. So I have a dy on this side, and I'm going to put dx over here. And I'm going to keep the 4x, right, on here, but I need to move the y squared to the other side. So I'm going to just divide it. And so that's the separation of variables. I'm going to integrate both sides. Well, this is the integration of y to the negative 2 dy equals the integration of 4x dx. So this is going to be y to the negative 1 over negative 1. And this is going to be 4x squared over 2 plus c. And so this is going to be negative 1 over y equals 2x squared plus c. My initial condition is the point 0, 1. So I have negative 1 equals 0 plus c. So now I know what c is. And so I'm going to end up with negative 1 over y equals 2x squared minus 1. And then in order to make that y equals, right, I'm just going to flip it over. I'm going to change, see if this is over 1, right? So I'm just, if I can, one of the rules of proportions is that if I flip over 1, take the reciprocal, I have to take the reciprocal of the other side. So negative y equals 1 over 2x squared minus 1. So y is negative 1 over 2x squared minus 1. And that's my original function. That's a particular function, general solution to this differential equation, using this initial value to obtain it. So on a slope field, that would just be one thing. It would be this graph that went through the point 0, 1. So here's the final example in this differential equation, right? Once I have my differential equation, I'm going to separate the variables. So I have dy, if I divide by x squared, so I have dy over y squared. And then if I multiply by dx, then I have dx over x. All right, so take a second to look at what I did there. You could also cross multiply. I think I would rather divide both sides by y squared. So this one, if I divide both sides by y squared, then this is going to cancel, so there's no y squared on this side. The y squared is divided on this side, and then I'm just going to multiply by dx. All right, and so the next thing I need to do is integrate both sides. So this is going to be the integration of y to the negative 2 dy equals dx over x. So this is going to be y to the negative 1 over negative 1 equals the natural log of x plus c. My initial condition is 1 and 1/3. So I would have negative 1 over y equals the natural log of x plus c. Okay, so I put in x is 1, and this is 1/3. Well, if you divide by a fraction, I'm going to end up with negative 3 equals the natural log of 1, which is 0, plus c. So my c is going to be negative 3. So my equation is, once again, 1 over y equals the natural log of the absolute value of x minus 3. And then, once again, I'm going to do the same thing I did before. If I flip it over, do the reciprocal, this will be 1 over the natural log of the absolute value of x minus 3, and then minus. So once again, this is a particular solution through this point of that differential equation. All right? So we're going to practice this in class, of course. So I hope you took good notes, and I will see you then.